Then you fix on this term, the tau yz is equivalent. This one, it means equivalent to this one minus. Here again, the tau yz minus tau yz is equivalent to that one, so I remove the minus sign to that side. So here appear the minus sign. Okay. And this one, basically, because we have the analytical solution, the expression of the diffraction, so we can calculate this term. This one basically equal to P over S and X times X. And again, we can utilize the analogy this one. So basically, we can make an additional equivalent. This one, P over S is equivalent to 2G beta X. So therefore, tau yz equal to 2G beta X. And if you like to rearrange, you can replace the 2G beta in terms of torque. So basically that is a 2T divided by Gx. Okay?
What does the X refer to?
The X is the locations, the coordinates.
Okay.
Yeah. So it depends on which point you look at, and that is the location, the coordinates of the X. And tau xz is equivalent to this term. And from our beginning, we assume that in this region, let me call it this region A, the region A. How about that? In region A is 0. Okay. So
quick question.
yes.
What is that previous called? I don't know. Okay, so the partial derivative is zeta over dx. The negative partial derivative, that in itself is defined as p.
Here, from here, this one.
Well, that. But where are you getting, like, deriving that equation over?
Yeah, this one.
Oh.
This one is from here. Right?
Oh,
we can take
okay.
the derivative from here. So basically here, let me make a note.
No, yeah.
So that means this one, partial x equal to p over s times x.
Oh, yeah. Sorry, yeah,
Okay.
I didn't realize where you were pulling that from.
So like this one, and so that means the magnitude from this equation, so that means in region A, the magnitude will be equal to the one yz squared plus xz squared, and that one basically is equal to this one. And here, because we take here, so the coordinates, we take the absolute value of the x. Okay. And because here we're looking for is the magnitude. So the magnitude is equal to this one, and you can see. So let me write it up here. So the maximum, the magnitude, and it has the maximum where? So looking at this one, is 2t divided by j, and when the maximum is when x reaching to its maximum value. So for this case, you can see the x, the maximum would be when x equal to maximum in the domain. That means here and here, when x equal to positive or negative h over half. Okay, so that means this is when x equal to this one. Okay, so that one would be equal to t h over j.
That's tau magnitude.
Are we okay? And then let me rearrange this one. So basically this one, let me rewrite this one. TH, and what is J? J is 1/3 BH cubed. So basically this is T 1/3 BH squared. For this example, I just try to do some calculation. So right now from here we can label it. So right now you can see the maximum basically is here, about in region A and on the top and the bottom here. Right. So here we're working on this number is in the region A, and now we identify the maximum is where and here. So and here basically is on the top and the bottom here, and that is where is the maximum of the strain stress. And this value, we have the number is T over 1/3 BH squared. Right. Looking at your lecture notes,
Is it BH cubed or BH squared?
BH squared, because here we cancel one H. Yeah. And so right now, this one, I can eliminate this one. So compared to the first portion of this chapter, the first portion of this chapter, and that is the formula. Two formulas provided in our textbook with a table associated with C1 and C2. Do you remember that formula? And dig out your lecture note with the